Hey everybody, this next video lesson is going to be the first video lesson of this next chapter. This chapter we're going to explore the different kinds of bonds that form between atoms. Before we talk about the bonds that form between the atoms though, we need to talk about something called the valence electrons. These are the electrons that are the most important electrons when it comes to forming bonds. Now I have a picture of the periodic table up here because I'm going to reference some of these elements as we go. But let's take a look at lithium. Lithium has 3 protons and 3 electrons. I learned that last chapter because I learned that the atomic number of lithium is 3 and it's neutral, and so for every proton it has a number of electrons. Now there's a nucleus with 3 protons, but those 3 electrons are outside of the nucleus, floating around. But there are rules of nature that say that these 3 electrons can't be all on the same level. They all can't be on the same ring. Now around any particular nucleus, in fact all nucleus, have these rings around them. Now whether or not they have electrons in those rings, well, that's a different story. But all atoms have a set of rings that are kind of circles inside of circles inside of circles. Imagine these rings as levels in a hotel. Now, there may not be people in those rooms on the hotel floors, but they still exist. These rings are places where electrons are going to live. Now, these rings might not have electrons in them, but they exist. Every element has a set of rings around it where electrons could live if it had electrons to put in there. We call these rings energy levels. On the first energy level, it's really small and close to the nucleus. The first energy level is so small that only 2 electrons can fit on the first energy level. Now the second energy level is a little bit further away from the nucleus, and it's a little bit bigger. As you can see, the circle is bigger. So on the second energy level, which we'll call N, energy level N number 2, you can have up to 8 electrons on that ring. Now the third energy level, which I'll highlight in green here, can hold also 8 electrons. And once you get to the 4th ring, or the 4th energy level, now it's really, really big. And it's so big, and I'll highlight it in red here, that you can fit up to 18 electrons around that ring. Now, not every element is going to have enough electrons to fit into the 4th ring. Let's go back to lithium, for example. I drew 3 electrons around the first ring of lithium, but the rule says that on the first energy level only 2 can be there. So I need to erase one, and let's do that right now. I'll just erase this and then redraw this ring. But since the first 2 are on the first ring, I need to form another ring, and now I can put the 3rd electron of lithium over on that second ring. You will be expected to know how many electrons can fit on each of the energy levels. So this might be something that you want to make flashcards to help you memorize. Furthermore, I'd expect you to be able to draw an atom with its electrons properly placed in the energy levels. So if I say, for example, take boron, which is number 5 over here, and you can see boron's got 5 protons and it's got 5 electrons. Now we know it's got 5 protons, so we're not going to draw the 5 protons, but we will expect you to draw the 5 electrons. So maybe I'll put B for boron in the middle here to represent the nucleus. Now I need to place those 5 electrons. Now the first 2 electrons can go into the first energy level, but then it's full. Now there are 3 more electrons to place. Now the question is, can I place all 3 in the next ring, or will I need a 3rd ring? Well, if I go over to my chart here, the second energy level can hold up to 8. So between the first and the second together, you can add them together. The first 2 energy levels can hold up to 10. So boron has 5 electrons, so the remaining electrons can fit comfortably on the second ring. So 1, 2, 3. And I double check and count them. I have 1, 2, 3, 4, 5. That matches the atomic number of boron, so I know that I have the right number of electrons. And I know that it's correct because there's 2 on the first ring and 3 on the second. I can't put them all on the first ring because the first ring is full at 2. Let's do one more example, and then I'll do one, and then I'll let you try one, see if you got it. So let's pick an element off the periodic table that has maybe 9 electrons, like fluorine. Now the first 2 electrons go on the first ring. So I will draw fluorine in the middle. Now that's 2 electrons, but I need 9, so I need 7 more. Now the second ring can fit up to 8, so it's good. I won't need more than 2 rings. So I draw another ring in, and then I add 7. 1, 2, 3, 4, 5, 6, 7. Now if I needed any more than 8 on the second ring, then I would have to draw a third ring. Maybe let's take and do that. Let's do one that needs a third ring. So instead of making this fluorine, let's say this is magnesium, Mg. Now magnesium is right over here. It's number 12. And so I have 12 electrons that I need to place. So going back to the ones that I've already put, I got 1, 2, and then 3, 4, 5, 6, 7, 8, 9. And then I can put one more electron on this second ring. That makes 10. But now I've run out of room on the second floor, or the second energy level, because it's a hotel. So on the second floor, all the rooms are filled. So now I have to put my next guess on the third energy level. Well, my first 10 went on the first 2 energy levels. Now my last 2 can go on this third energy level. Now this third energy level can also fit up to 8 electrons. And so 2 fit comfortably, and I can fit up to 6 more. But I don't need to, because I'm just working with magnesium. So I'm going to clear the page now, but you'll probably just want to move to a clean part of your notes in order to write this next part down. But I want to keep the periodic table in view, so I'm just going to take the rest of this stuff out to give myself space to write what I want to talk about next. So the next thing I want to talk about are those things that I mentioned earlier. They're called valence electrons. Now, as I mentioned before, valence electrons are the most important electrons for bonding. And what makes them valence electrons is that they are the furthest ring away from the nucleus. That is the definition of a valence electron. They are electrons on the furthest ring or the furthest energy level from the nucleus. So if you take my example that I left on this sheet here, magnesium. Magnesium has 12 total electrons, as we can see from the periodic table, but not all of them are valence. If you only count the electrons on the farthest ring away, then it only has 2 valence electrons. Now I've already told you that the periodic table is pretty much magic, but this is one of the many magic tricks that I'm about to reveal to you that has to do with the periodic table. You see how magnesium is in the second column? And I just told you that magnesium has 2 valence electrons. Like you can see it in this picture, it only has 2 dots on the furthest ring. Now, let's take a look at beryllium to illustrate my example. Beryllium has 4 total electrons. Now, if I do beryllium's rings, beryllium has 2 on the first ring, and then its next 2 go on the next ring. Well, look at that. Beryllium is just above magnesium, and it also has 2 valence electrons. That is not a coincidence. That is by design. In fact, the periodic table is set up so that elements in the same column all have the same valence electrons. Now, beryllium is a smaller element, so it has less rings, but the fact that its last ring has 2 valence electrons is the same as magnesium with its 2 valence electrons. Now, calcium would have 3 rings, and it would have 2 valence electrons in its last rings. Strontium would have 4 rings, but only 2 in its last ring. Barium would have 5 rings, and radium 6. You see, as you go down the column, you add a ring, but you always keep the same number of electrons in the outermost energy level. So over the top of this column, I'm going to write 2VE for 2 valence electrons, because all of these elements have 2 valence electrons. Now, this isn't the only column on the periodic table where it has this awesome pattern. In fact, all of the columns in the periodic table, with the exception of the transition metals, show this crazy, awesome pattern. Take a look at the first group of elements, the alkali metals, these all have one valence electron in their furthest energy level. Now skip over to boron and friends, and you'll see that boron has 3 valence electrons. And in fact, we already drew boron, and I showed you that it has 3 valence electrons. Now everything underneath boron will also have 3 valence electrons. Carbon will have 4, nitrogen 5, oxygen 6, and fluorine 7. See, the valence electrons get 1 larger every group you move to the right. So 3 turns to 4, 5, 6, 7. And the last group, the noble gases, have 8 valence electrons in their highest energy level. Now notice that I drew the arrow pointing to neon here and not helium, because helium doesn't have 8 valence electrons. In fact, it doesn't even have 8 total electrons. You see, its atomic number is 2, so it only has 2 electrons. But remember, the first level is filled at 2. And so helium's full valence electron shell fills up at 2, but everything else below it fills up with 8. But 8 is the maximum amount of electrons that you can have in the second and third ring, and so these elements all have full valence energy levels. That is the magic of the periodic table. The columns are organized by valence electrons. Now that you know that the pattern for valence electrons exists, you no longer have to draw the picture to be able to figure out how many valence electrons something has. If I just say, for example, maybe list an element and just say, all right, potassium. How many valence electrons does potassium have? Well, you locate potassium on the periodic table, and it's right here in the first column. And because I wrote this over my periodic table, I know that everything in this column has 1 valence electron. So just simply because of its position on the table, I know how many electrons it's going to have in its highest energy level, 1 in potassium's case. Now, you can't do this for the transition metals, and so we skip them. If you were ever asked to identify the valence electrons for one of the transition metals, you can't do it. But you can for the first 2 columns and the last 6 columns of the periodic table. So let's do another one. Let's do bromine. How many valence electrons does bromine have? Well, you locate bromine on the periodic table. It's right here, and you look up at the top of the column, and what does it say? It's got 7 valence electrons. So, easy peasy, lemon squeezy. Put a 7 there. Last one I want to do for you, before I let you try a couple on your own, is phosphorus. Well, how many valence electrons does phosphorus have? So I find phosphorus. Oh, there it is. It's number 15. It's got 15 total electrons, but only 5 of them are valence. And so I put a 5 in the blank to represent the number of valence electrons for phosphorus. Well, that takes care of this video lesson on valence electrons. Thanks for watching.